Okay, today we're looking at polynomial functions and rational functions. Our objectives for today are determine the behavior of a graph of a polynomial function using the leading term test, factor polynomial functions and find their zeros and their multiplicities, and solve applied problems using polynomial models. So if you look here, this is a standard polynomial function. So remember, each of these, a to the n, could be any number that's in front all the way down to we just have our whatever that constant may be. And our x powers, okay, whatever that n is, that's the highest number. So like if it was to the 4th power, then the next one would be to the 3rd power. And the next one would be to the 2nd power all the way down until we have no x's at all because we have our constant. Okay, so all of the a's again are just real numbers, and then the exponents are whole numbers. Remember, this makes a polynomial. Okay, so here's an example of a polynomial, x squared minus 2x minus 3. Okay, in order to do this, this is a quadratic function, so we know that this makes the parabola shape. To find our zeros, you can factor this and see that our zeros are at -1 and 3. So if we want to write those as x-intercepts, we have -1, 0 and 3, 0. And then our y-intercept, if you were to plug 0 in for x, you see our y-intercept is at -3, so 0, -3. Since the parabola opens up, we have a minimum at -4. Okay, and this is when x equals 1. So that is your axis of symmetry that cuts the parabola right in half. Okay, there is not a maximum. And then, of course, our domain is all real numbers, so from -infinity to +infinity. And our range, our lowest y value is -4, and it's included, so we use the square bracket all the way up to +infinity. Okay, so those are some of the things that we would look at for these functions. A cubic function, remember, has this S shape. Okay, so at most it can have 3 real roots. Could possibly just have 1 root, okay, or even usually if it has 2, then it has 3. Okay, or it's possible that it only has just the 1. Okay, so remember, it goes down in multiples of 2. So we could have 3 or 1. Okay, this is going to have at least 1 root no matter where you move it. So we can factor this, and this one, okay, they've factored it for you there. Remember, there's several different ways that you can factor when there are 4 terms. One way is we can try factoring by grouping and see if we can factor it that way. Or we can, this one's already done for us. So we can see here that our zeros are at -4, -1, and +3. So that makes x-intercepts at -4, 0, -1, 0, 3, 0. Our y-intercept, notice again, if you plugged in 0 there, we would only have -12, so 0, -12. Then this time we have some relative mins and maxes. So we have this relative max and a relative min right here. So those are listed at -20.7 when x is 1.4, and at 12.6 for the maximum when x is at -2.7. Okay, for these, we still have all real numbers. You can plug in any x value into this function. And notice, since it starts down and ends up, then for our range, we also have all real numbers. Okay, here's some other examples of polynomial functions. So polynomial just means many, right? And so sometimes we have a squared, sometimes we have a cube. Okay, we can even have a 4th. Even if there's not an x, we have 0 x's, or 0 x squared, or there's not any squareds or any x's at all. This is just a constant, okay? Still a polynomial. So lots of different types of polynomials there. Okay, these are non-polynomials, okay? Absolute values, radical functions, functions where we have it raised to a power that is a fraction or if we get something like this where we're doing x's in both the numerator and the denominator, these are non-polynomials. So the graph of a polynomial function is continuous and smooth. That means it goes on forever, right? And smooth, there's no sharp points like we saw in some of those previous examples. The domain of a polynomial function is the set of all real numbers. So you can plug in any x. So the leading term test. Okay, so this is how we can determine from the first term how our end behavior should look. Okay, so we have these 4 different possibilities. So when we have an even exponent, okay, for your n, so notice this is x to the n power, when it's even, like 2 or 4 or 6, something like that. Okay, if your a to the n, so this is your number in the front, is greater than 0, okay, so basically if it's positive number, then it's going to end up on both sides. So as we go to negative infinity, it's going to positive infinity. As we go to positive infinity, it's going to go to positive infinity. Okay, so think about a parabola. If it is positive, it opens up. Okay, if it's the 4th power, it opens up. Okay, if it is less than 0, so basically you're saying it's a negative in the front, then obviously that makes it flip over and you'll end up with down, down. Okay, remember odd functions like cubes and fifths and so forth, okay, always have opposite. One's down, one's up. Okay, here's the normal. So when it's positive, it starts going down and it ends up. Okay, well, if it flips, so if it's negative, it should be the opposite. It's starting at the positive and ending at the negative. Okay, so starting up and ending down. Okay, and of course, that squiggly line portion of the graph is not determined by the test. So it depends on what the power is on your x, how many times it can go up and down in the middle. So basically, we're just looking at the end behavior for these. So let's use the leading term test and match each of the following functions with one of the graphs A through D. And again, these are the ones, in your notes. So we have these 4 graphs. Okay, so let's look now at the pictures of the graphs and see if we can tell. First thing you want to look at is what is your greatest power. So we can see that A has a 4th power, B has a 3rd power, C has a 5th power, and D has a power of 6. So let's start with the even powers, the 2 and the 6. Okay, so if these are even, we know that they should be the same. Okay, so that's going to rule out graph A and graph B because they don't end in the same position. Okay, let's look at A. This one has a number greater than 0, so it's positive. Okay, so even though this could go up and down in the middle, we know that this should open up. Okay, so that means A has to match with D. Okay, so then if we jump down here to D, okay, it has a negative. So whichever way the end behavior is ending, they should be pointing down. So this would have to be C because they are going down. And again, in the middle, it can go up and down several times because of that 6. So at most, you could have 6 real roots. Doesn't mean you necessarily will. Okay, just by looking at that graph, it looks like there's just 2 actually. Okay, so then let's look at these other 2. Okay, these are odd, so one should be up, one should be down as far as your end behavior. If it's negative, okay, it should be flipped. It should start up and end down. So that means that B matches with B because it starts up and ends down. And so this one, since you're 1 in the front, okay, because there's always a 1 there, if there's not a number, is greater than 0, so it should start down and end up. Okay, so like we said, your A matches with graph D because it's even and positive. And then your B matches with graph B because it's odd and your number in front is negative. And then on graph C, it's an odd term there and positive in the front because that is greater than 0. And so that graph matched with graph A. And then the last one, because you had the 6, it's even, and in front it's negative, so we matched it with graph C. So make sure you've filled that in on your chart. Okay, finding zeros of factored polynomial functions. If C is a real zero of a function, okay, so that's if you plug in whatever C is and it equals 0, then C0 is an x-intercept of the graph of the function. So let's see what this is talking about. So if we are to find the zeros here, notice that we have 1, 2, 3, 4 different possibilities here, but 3 of them are the same. Okay, so right there we can rewrite that. Instead of writing all 3 of them as x minus 3 to the 3rd power and then x plus 2. Well, we're just going to change the signs on each of these in order to find the zeros. So we get x equals 1 and x equals negative 2. So then there's the x-intercepts are at 1, 0 and negative 2, 0. And there's a graph that shows that yes, you could have up to 4 because there are 4 different x's in there. But since we have 3 at the same number there at 1, then we only end up with 2 intercepts on the actual graph. Okay, let's talk about even and odd multiplicity. Okay, so if x minus c, in parentheses raised to the k power, and here remember it's got to be greater than 1 to be a polynomial there, and we have this, and this is not a factor. Okay, if k is odd, then the graph crosses x at whatever that c0 is. If k is even, then the graph is tangent to the x-axis at whatever that point is. Okay, so let's look at what this is talking about for even and odd multiplicity. Okay, so here we have this equation. Now remember, when we have 4 terms, the easiest way to factor is to group and go through and factor. So I'm going to first group by factor by grouping. So notice I just grouped the first 2 terms and I'm grouping the last 2 terms. Okay, anytime you have a negative in front of that term, you want to group it. We are not saying that these multiply. Okay, we are just showing how we could group. So I'm going to pull out the greatest common factor. So here x squared, which leaves me with x minus 2. And here the greatest common factor is negative 9. So you always want to pull that negative out with it. Okay, and then that changes this to x minus 2. The parts in parentheses must match when you factor by grouping. Then you'll recall from Algebra 2, we take what's in the front and write it in one parenthesis. And then we only write one of the part that's in the parentheses. You do not write 2 of those, okay? Because think about going through and distributing this. Okay, it would be the same thing as foiling this. Okay, so this and this equal the same thing, but now we've written it as factors. Okay, well this first part is the difference of squares, so we can factor it further. So we get x minus 3 and x plus 3. So now this is fully factored, and so to solve, we're just going to change the signs on each of those. So we have the x can be negative 3, 2, or positive 3. And these can be written in any order. I just like to write them from least to greatest, just my preference. And then you can see there how they each go through. Because like they said, okay, if you just have one of them, then it's going to pass through. I have one of each of these, so it's going to pass through at each of those points. So it's going through the graph at each of those points. Okay, let's try factoring this one. Okay, when you have x to the fourth, we can use regular factoring. It's just that when we factor the x to the fourth, we're going to end up with an x squared in each. Okay, and then we're just asking ourselves what multiplies to 33 that also adds to 8. So that's where, or not adds to, subtracts to 8. So we get a 11 and a negative 3. That's going to give us the 8 in the center. Okay, well, if we look at this first part, that can't simplify anymore. Even though this has a minus sign, 3 is not a perfect square, but we can see if we can find other numbers that could work in here, okay, by taking each of these and setting them equal to 0. So we move the number to the other side for both of them, and then of course we're going to square root each side. Okay, and remember, when we square root, we get both the positive and the negative of each of those numbers. So there's my solutions. Positive, negative, square root of negative 11, which, what kind of thing does that give us? It gives us an imaginary number because of the negative. This one, square root of 3, doesn't simplify, so we simply leave it as that. Okay, so we're only going to see actually these two on the graph. Now, if you wanted to see what that was, we know that square root of 3, is like 1 point something something. Okay, it's not quite a whole number there. We know that 4 would give you 2, so we know it's between 1 and 2, closer to the 2, okay, that would actually be crossing through the graph. Okay, so if you look at that, notice how they're close to the 2, but if you were to plug in, it's probably approximately here and here. So we got these other two, but these are imaginary, so they're not actually going to show up on the graph. Just those two real roots. Remember, we're only going to see real roots crossing on the graph. Okay, and there's the approximation for square root of 3. Okay, here's another polynomial function. Okay, so if we look at these, it says this equation can be used to estimate the number of milligrams of the pain relief medication ibuprofen in the bloodstream T hours after 400 milligrams of the medication has been taken. Find the number of milligrams in the bloodstream at 0, 0.5, 1, 1.5, and so on up to 6 hours. Round the function values to the nearest tenth. So you're going to want to make yourself a table where you can have your x values and your y values. So with your x values, you're going to want to put in 0, 0.5, 1, 1.5, 2, 2.5, 3, all the way up to 6 hours. So I'll give you a moment to make yourself a table. Okay, and once you finish creating your table, you're simply going to substitute that into the equation. So if you're using your calculator, first you're going to plug in 0. Well, 0 for each of those is just going to give you 0. So obviously, before you've taken the medication, you have no medication in your system. Okay, well, when it's been 0.5 hours, so half an hour, how much medication is in your system now? Okay, you're going to get a graph that looks like this if you were to graph it. But let's look at the table of values. So at 0, we have none. Oops, that looks like my thing is messed up. That should be over there. That's 150.2. The 150.2 should be your milligrams of ibuprofen that's in your system. Obviously, I need to fix this. Okay, for 1, we have 255 milligrams would end up over here. For your 1.5, the 3.18.3 should end up right there. For your 2, your 344.4 should end up here. My spacing got off somehow. 2.5, your 338.6 should end here. And for 3, we see 306.9. For 3.5, we're at 255.9. So somewhere in here, we've hit our peak, right? So we don't know exactly, we know it was going up till it got to this point, and now it is going back down. which makes sense. You know, once it's been in your system, it starts to dissipate. So at 4, we're at 193.2. At 4.5, you're at 126.9. At 5, we're at 66. 5.5, we're at 20.2. And then at 6, notice we're at 0. Okay, so it goes into your system, and it's going to take about 2.5 hours or so, or about between the 2.5, it's going to get your highest amount. Okay, so that's why they usually say on recommended dosage that after 4 hours, okay, if you look at 4 hours, we're at 193.2, okay, it will start, if you take another dose, you know, you're never going to get too much in there if you wait that 4 hours. If you take it sooner, then you may be overdosing. Okay, but it's going to like go up, and then you could make it stay constant if you take another dose around 4 hours. Okay, because after 6 hours, the medication is completely worn off.